Okay, our presentation is on how is COVID-19 different than other strands. This is by group 911. Today we'll be covering the anatomy of and treatment of 3 different strands of coronavirus upon and we're going to be looking on the differences and some similarities to see if there's anything that can help us cure COVID or just make vaccines or anything better. So COVID-19, it's a single-stranded RNA virus, and the S gene, or the spike protein, in COVID-19 is way more divergent than any other strands of COVID. The spike protein can bind host receptors together in varying ways and cause many mutations at the same strand of COVID. The major differences in COVID-19 are the 3 short intersections in the N-terminal domain, which sometimes confers to celiac acid binding activity. And 4 out of the 5 key residues changes the receptor's binding motive, which is different than SARS-CoV. COVID-19 is another beta coronavirus, meaning that their spike protein is what causes most of the issues, making the viruses so unpredictable. So the first strand of COVID we will be comparing COVID-19 to is SARS-CoV. SARS was a severe acute respiratory syndrome. It caused a pandemic in 2003. It was contagious and sometimes fatal. There is no known transmission of the strand anywhere in the world since 2004, though. It had flu-like symptoms similar to COVID, and it also belongs to the beta coronavirus family. The SARS coronavirus targets the epithelial cells of the lower respiratory tract, resulting in severe alveolar damage. This strand was also identified as the novel coronavirus, which was identified as the origin of SARS. This virus, SARS-CoV, belongs to the family of single-stranded RNA viruses like COVID-19, and has genomic characterization showed that the SARS is only moderately related to other known coronaviruses. And that's a picture of basically what SARS-CoV looks like. It's also known as SARS-CoV-1. So for treatment and vaccine information on SARS-CoV, there's no commercial vaccines currently available for SARS-CoV strand of coronaviruses. These studies tried to target the spike glycoprotein, which was mentioned in the previous slide, and it's the reason coronaviruses are attacking human cells. Through this information, it has been crucial to the what we're finding for COVID-19, and we use this information of the spike glycoprotein in the vaccines for COVID-19, considering the similarities between SARS-CoV and SARS-CoV-2, which is also COVID-19. It also has the same treatment methods as COVID-19, respirators, oxygen management, and other care, because there's no cure for this either. Some ways the spread of SARS was slowed and eventually stopped is that there's some difference of SARS-CoV because it was an epidemic. When looking into this, there wasn't much we learned about similar methods we were using, such as social distancing, masks, etc. And it was not as bad as COVID-19 was. The spread wasn't. All right, on to Alex.
All right. So another thing we were looking at was MERS COVID, which also had some different treatments and stuff like that. That also had several different vaccines that have been created and has been seen since the appearance of MERS in 2012. Like the SARS, the MERS also goes for the glycoprotein. When digging deeper into the information, we did find out that the SARS-CoV virus was better for collecting information, for solving anything we could do with COVID-19. But the treatments contain just same stuff as you just need some rest, drink some fluids, sometimes have some painkillers as well. But it was also with some oxygen treatments here and there. When someone tests positive for MERS, though, they have to quarantine as well, just like you do now, till they no longer present the illness. again, this is the same stuff we do with COVID, which we've already been trying to do, and as well as wearing the masks to try and stop the stuff spreading through the air as well. So we go on the last slide here. Then we have the conclusion here. Yeah, in conclusion, we did check out all 3 of the strands of the virus spike proteins causing mutations and all other deformities to the human cells occur. Though with the SARS-CoV and SARS-CoV-2, both caused mainly respiratory stuff within the breathing system symptoms as well, but MERS goes for other organs such as the liver and kidneys. So they both target different things within the body. They're not exactly the same here. Both SARS and SARS-2 were passed to humans by bats, which is a little bit similar to what's going on with COVID here, where MERS was passed from camels. But for all of the beta coronavirus spike proteins, the common target for the antibodies is creating vaccines. And that's pretty much it. Then we just have all of our sources here.